So hi everyone. Before I introduce Davide, I want to introduce myself because I've been here for like 2 weeks. I'm a new postdoc. I'm Katie Breivik. You can find me in 1304. All right, so our seminar this week is from Davide Gerosa. He is currently an Einstein Fellow at Caltech. He did his PhD at the University of Cambridge in the UK, and today he's going to be telling us about all of his work that he does on black hole recoils.
Thanks, Katie, and thanks everybody for the kind invitation here. It's my first time in Toronto, actually my first time in Canada. So this work that I want to present today, it's kind of a cross-section of a bunch of papers and results that we put out in the last 3 years or so. And this is done in collaboration with all these folks listed here. And I like to notice these guys that I stressed are all undergraduate students that I had the extreme pleasure to work with in the past 3 years or so. They all did summer projects with me in Cambridge first and then at Caltech more recently. So this is all about black hole recoils or black hole kicks. And I'll be going through some of the physical and astrophysical consequences on these fascinating events. So here is a brief outline of my talk. First of all, what black holes recoils are. Then point 2, how do you model them? How do you get them out of simulations that we do and stuff? And I'll be showing how this is all encoded in a gravitational waveform. And then I'll go a little bit deeper into the astrophysics, asking whether superkicks or the large recoils that can eject black holes from their galaxies, whether they're real, whether they actually can exist and can be predicted in realistic astrophysical environments. And here we will need 2 steps. A first phase where the main effect that determines the recoils are the spin alignment via accretion disk, and later a post-Newtonian evolution to bring the binaries to merger. And if I have time, I like to sketch some of the more exotic idea of direct detection of black hole kicks using gravitational wave experiments. OK, so black hole kicks or recoils. So it's basically momentum conservation applied to black hole mergers. And that's almost everything one has to say about it. So the scenario here is that you have 2 black holes that are merging. And for some reason, the binary is asymmetric for, say, one black hole is more massive than the other one black hole is spinning, the spins are misaligned, or whatever. So if you don't have 2 identical objects, the gravitational wave emitted will have some preferential direction that just reflects the asymmetry that is written in the systems. So gravitational waves are being emitted in some anisotropic fashion, and gravitational waves take out linear momentum from the system. They take out energy and angular momentum, that we know they're causing the in-spiral of the binary, but they also take out linear momentum. So if you're emitting linear momentum somewhere, conservation of linear momentum implies that the center of mass, or if you want, after the merger, the final black hole, has to recoil in the opposite direction. That's the main idea behind black hole kicks, and the surprise is that these guys here, these kicks here, are large. So if you have non-spinning black holes, in that case, the kick is only due to a difference in the masses between the 2 black holes, and kicks can get up to 160 or so kilometers per second. When you start having spinning black holes is where the real fun begins, and people have predicted with various names. I'll be called this guy superkick. That's what people use in the literature. And recoils are as large as 5,000 kilometers per second.
So where did the scale of 160 kilometers per second come from? Because the only velocity scale in the problem that I can see is the speed of light.
It's the mass ratio. It's some factor of the mass ratio. It's a fraction of the speed of light weighted by the mass ratio. So and it's 1 over 1 plus q, whatever.
What mass ratio gives you the largest velocity, right?
It's like
then you shouldn't get a kick.
It's like 0.25 or so. There's a maximum in between, you're right. So in the test particle limit, you have a particle plunging into a black hole and no kick. In the equal mass non-spinning limit, you have no kick by symmetry, and the maximum is somewhere in between, 1 to 4 or so. So if you start playing with spins, kicks can get much, much larger, and in particular up to thousands of kilometers per second. And here are some results. So these are kicks or various predictions or so. This is the mass ratio, the symmetric mass ratio. So here it's equal mass black holes. Here is test particle limit. And this is the maximum velocity that the black hole kick can get. And you see it's up to 5,000 or so kilometers per second. There are two things I'd like to point out here before going into more details. So first of all, the velocity in GR, a velocity is a dimensionless number. It's just a fraction of the speed of light. And the total mass is just a free scale. So you get the same kick if you have 2 10 solar mass or 2 billion solar mass black holes merging into each other, provided that the dimensionless parameters, so the mass ratio and the spins and the misalignments or so are the same. Everything is just scaled up and down. One thing that this numerical relativity simulation highlighted is that to get large kicks, you critically need a few things to happen at the same time. You want the two black holes with kind of similar black hole masses, so to be in the equal mass limit when you have strong field dynamics, high spins, because you pump up the spin effects only if the spins are large. Large spin misalignment. So people found that large kicks only happen if the black holes merge with spins which are largely misaligned. If the spins are both aligned with the orbital angular momentum, kicks are down to hundreds of kilometers per second. Moreover, you also want to be kind of lucky with the orbital phase at merger. So you want the two black holes to plunge like this and not like this, so with pi difference or so. So super kicks, or these large kicks, might be kind of fine-tuned in the sense that you need all these things to happen at the same time. Yes?
Is there a simple physical reason for that?
Yes, it's frame dragging. So if you have two black holes like this, the frame dragging of each black hole, they act constructively. So the center of mass of the binary, I'll have a slide on this, oscillates up and down, and then at some point it stops. So you kind of want all these things to happen at the same time. So one might think that the super kick problem is actually a fine-tuned one. And these things actually don't happen in the real world. So why are these large number important? Well, they can get larger than the escape speed of the galaxies, of actually all known astrophysical hosts. So in this plot here, there's, as a function of the magnitude or the mass of the object, if you want, the typical escape speed of these guys. And we have, globular clusters down here, order of 10 kilometers per second, and the escape speed of large ellipticals, which are a few thousands of kilometers per second or so. So if following a black hole merger, think about a supermassive black hole merger now, the final black hole gets kicked out with thousands of kilometers per second. This would mean, that you eject, following a galaxy merger, you eject the final black hole. So if this happens, you can get black hole ejection and stuff. And of course, Martin Rees predicted it in the 80s. Even if kicks are smaller, a possible observational signature is the displacement of the quasar in the center of the galaxy. So, and this is, in my opinion, the most promising candidate. So this is an object that they've been observing over a baseline of like 60 years or so. And there's this off-center source, which is persistent. And it was initially believed to be a supernova remnant, but now it's kind of 60 years that they're seeing it. So the leading candidate to explain this observation is actually a black hole who's been recoiling. We know that this galaxy had a major merger, maybe some mega years ago, 10, 50 mega years ago, and this guy is being recoiling out of his galaxy because of a gravitational wave kick. So there are a few electromagnetic candidates, but so far no unambiguous detection, despite this one being the most convincing in my opinion. And one point I'll be touching base at the end is whether gravitational waves can actually help to directly detect black hole recoils. All right, so first point I want to mention is how to model these things and how to extract how big they are and describe the phenomenology of these black hole recoils. And so here is my scary slide with all the equations. So as I was saying at the beginning, kicks are there because you are emitting linear momentum through gravitational waves. So everything that you need to model black hole kicks is in the gravitational wave strain or the waveform. So we usually break it down into spin-weighted spherical harmonics power. And one important thing is that one might be tempted to say, measure the center of do a simulation and measure the center of mass of the system and how it moves. But you need to be careful with coordinate. That's a very gaugy thing to do. One really needs to get the strain at infinity or where the extraction radius of a simulation is, extract the linear momentum there, and then do minus that, which is the linear momentum that has been dissipating from the system. So this is the flux of linear momentum P as a function of all the waveform modes and stuff. And there are two interesting things. Yeah.
So where Gross Newtonian?
No, this is full GR.
You can do this in full GR?
I mean, I don't do the simulation, but catalogs. There are catalogs of simulations available where they extract, where they basically give you, they run their simulation codes and they give you the strain decomposed in spherical harmonics mode. Actually, if you try to do it with PN, and they did it before NR was available, you get a very bad prediction for the kicks. While other things like the dissipation rate of energy and angular momentum are kind of good enough with PN, the kick all happens at the very late time, so only at merger, where you need numerical relativity to model it. Give me one slide, and then I'll.
I'm just confused because those are all ODEs, right? And usually when you have to do these things.
Yeah, sure, but this is assume that you have the modes. So you've solved the Einstein equation, in a computer or whatever. You extract the modes at infinity, and then these are just the expression to get the linear momentum flux out of those modes. And the flux is just proportional to the derivative of the strain. With the first time derivative of the strain, if you want, is the first time integral of the psi4. That's what they extract from the NR simulation. So two things to note here. So kicks are only present if higher harmonics are present. So there are all these L, M plus 1, L plus 1 or so. So you want to go beyond the standard quadruple modes. But even if you don't have higher kicks, if you have differences between the 2-2 and the 2-2 mode, that will impart a kick. So if you have more power in the 2-2 and less power in 2-2 or so, that will reflect in a kick. And crucially, if you assume this relation, which is the lowest order PN stuff that you can do, there are no kicks built in by construction. So you do need to go to either higher PN order, but that still kind of fail, or to pure NR to actually model black hole kicks properly. So people so far have been looking at these things by developing fitting formula to NR simulations. And well, some of the results I want to present today is extracting black hole kicks directly from the so-called numerical relativity surrogate models, which is a new and catchy way to directly model the strain by very smart interpolation schemes between large banks of NR simulation. So we've basically been leveraging the knowledge that was acquired by building surrogate model to construct black hole kicks approximately. We're not using fitting formula. So we're using the NR. So the NR simulation are interpolating to get the strain.
That's what I'm saying, you're interpolating.
Yes.
From the NR simulation.
We are. But we are interpolating a strain and then using the strain to get the flux. We're not fitting for the final kick directly, like people used to do. Right. All right, and then I'll use this thing to explain a bit of the phenomenology of this system. So, okay. So this is what happens for the so-called mass kicks. So if you have two black holes, the two have a different mass ratio. There's more radiation emitted, so the small guy emits more radiation in front of him. So there's a net motion of the center of mass in the plane of the binary, basically because the smaller object moves faster. So in this plot here, there's for a sequence of binary at varying mass ratio. So Q equal 0.5 is the light one, and Q equal 1 is the black line. There's this is the kick that a series of binary receives projected along x and y. These are two coordinates in the orbital plane, and z. There's the coordinate along the orbital angular momentum when there's nothing there, and that's because there's no. An equal mass system is symmetric up and down. And so here is a little animation of what the center of mass is doing. So this is actually the motion of the center of mass, as I was saying, obtained by integrating the flux and stuff from infinity, which is basically oscillating into the orbital plane. The merger happens at this location here, and then there's a last half a cycle, and then the binary recoils away. Interesting to note that everything, all the cake or so, happens at the times of almost about order of 10 in m up to merger. So close to the merger time, which is basically the last two orbits or so. There's virtually nothing going on before. So all the linear momentum flux is emitted very late, and that's why using PN approximant to try and predict black hole kicks, it's kind of inaccurate in the first place. Yes?
Is your Z component not completely zero?
Those are numerical errors. So this is actually boils down to the precision with which we are predicting kicks. But that's actually, this is 10 to the minus 5, the speed of light. It's actually a pretty good accuracy, given into the fact that we are not building in any symmetry by construction in the interpolation.
More than 10 to
That's a v in 10 to the minus 3 in C, so that's about 10 to the minus 5 C. All right, so what happened with spins, as I was saying before, the things get more complicated but also more exciting. Frame dragging comes into play. So now the physics is that you got two black holes. Assume you have two black holes merging with spins anti-parallel with respect to each other and into the orbital plane. So the orbital momentum is this way. The two black holes, like the frame dragging of the two black holes, acts constructively onto each other. So the center of mass of the system goes up and down in the z direction. And in this case, we basically have, because this is an equal mass system, we have no kicks in the orbital plane, so x and y, this is 0, and giant kicks, note that this is a factor 10 or so more than the other ones, in the z direction. So if you see the inset here, the center of mass is going up and down, but then at some point it has to stop because the binary merges. So for these two configurations, the stop happens when the velocity is very large, and so then they keep on going. For these other configurations, the stop happens when the velocity is small. So they stop there and alt.
It's
yes?
10M after the merger, right?
Yeah, so well, that depends how, so yes, but yes.
So the ring down actually produces a lot of
So it depends where the ring down starts and things and how you zero these things exactly. So these are zeroed with the total waveform amplitude. So the square sum of the modes. If you zero it with the 2-2 mode only, that's slightly over. The zero is probably right here or so. They typically say the ring down starts 10 to 15 M after merger, but yeah.
Do the spins process out of this anti-aligned configuration?
They do, but the precession timescale is much longer than the orbital timescale. So you need many orbits to capture precession. So precession scales in PN scales as separation to the 5 Alts, and orbit scales as separation to the 3 Alts. So in the few orbits, I mean, these simulations, they have like 20 orbits or so. There's not much precession going on there. Yes?
Do you assume an initially circular orbit?
We do, yeah. We do. So in this movie here, this is an even more complicated case. This is where I have two black holes that are spinning, and I also have a mass ratio. So this is the whole thing. So mass kick and spin kick all together. And what happens is that, well, this is at early times. There's not much going on here. You can kind of see the binary, which is orbiting, much like before, and then there's a complicated motion in the orbital plane. Mergers happens here, and this last swing is basically this super kick effect that you're seeing in this plot.
So what part of this orbit is interpolated and what is really calculated?
It's all calculated. Well,
you have the interpolation routine for interpolating.
we're interpolating the strain.
So there is an interpolation going on here.
Yeah, there are like thousands of points. For thousands of points, we compute the waveform, and the rest are interpolated.
I still don't understand. So what are you calculating and what are you interpolating?
So we have numerical relativity simulations. Those are used we extract waveforms from them. The waveform is interpolated, and this is other work done by others, mainly to construct LIGO waveform approximants. And for the duration of the waveform, the numerical relativity data are evaluated about 1,000 times.
I guess my question is, how do you do this integration?
The numerical integration is it's just brute force numerical integration.
So
Really?
Yeah.
brute force solving Einstein's equation.
Yeah.
For-
He's extracting. Other people extract waveforms, and then he's at finite times, discrete times, and
Yeah.
then he's interpolating along those discrete times. And then he's using those waveforms to get
the fluxes, to get the linear momentum flux. Thanks. All right. So you're basically seeing here the mass kick with this little oscillation, and then at some point the super kick effect kicks in and gives you this last swing. All right. So here's some more results on modeling the shape of the kick and stuff. So here I'm taking a single binary, and I'm projecting the kick along different direction. And so basically you see that, depending on where this last oscillation stops, you can get a final kick down here, which is either very large or very low in the opposite direction or 0. That's what I was saying before, that the orbital phase at merger actually matters. Depending on which orbital phase you're seeing and where you're seeing the kick from, the projection of the kick along your line of sight will be largely different. But it turns out that big kicks are simple. So in this plot here, I have a whole average of binaries projected on random binaries projected on random directions, and the color of these lines is basically the speed of the kick, and then I normalized everything such that they go to from 0 to 1, because I want to highlight the shape. And it turns out that the big kicks, so the ones that go all the way up to thousands of kilometers per second or so, they are actually very simple. They tend to follow, this is a nerve function that I put on top, meaning that the velocity is a nerve function, so the acceleration is Gaussian. So big kicks are actually very simple to model, which would be useful for what I want to say later. So it's a complicated problem, but it turns out that in order for the kick to be big, it also has to be simple.
Everybody asks the same question.
Yeah.
So if I have two identical black holes, maximally spinning, and don't you have perfect reflection symmetries, meaning that there's no axis that can possibly kick into?
If you have two black holes with spins like this, there is not, right? Because this guy and this guy, so if you flip the binary, so z to minus z, the rotation of the two black holes will not be the same.
What do you mean by that? Your two hands,
yeah.
two white hands, one spinning this way,
Yes.
one spinning that way.
Yes. If they merge like this, so what happens is that, as I was saying, so the center of mass goes up and down. So it is true that this motion is symmetric, but then at some point it stops. So if it's
But under true symmetry, then I have the explicit reflection symmetry along every axis. And the true symmetry, maybe it's some tiny violation that.
So if you have two black holes like this,
They plunge radially.
what?
They plunge radially.
And they plunge radially, is there a kick? I think there is.
Which direction?
But
I mean, you've got perfect reflection symmetry.
you're perfect, yeah.
I don't see how you can.
Maybe that's. Now I'm getting confused. Maybe that's the orbital phase that gives you a zero kick, and you need some. No?
It's a radial kick. It's a radial plunge.
They do find kicks for equal mass anti-aligned spin like these are actually the ones that give you big kicks. So it was this case here. Now, where is it? So this case here was actually, so Q equal 1, two spins of 0.8, left, right, meaning that the black holes start on the, one pointing to the left and one pointing to the right on the x-axis. That situation has a kick.
Which way is that? Which way is it?
What you're saying is they orbit like this, right?
They orbit like this.
Oh,
Yeah, exactly.
So this breaks the symmetry.
Yeah.
Exactly. And that's what he's saying. If you go like this, you get no kick.
Yeah.
That's why you're getting a Gaussian, I guess, because you're just orbiting. You're just going around the plunging phase, and that gives you that Gaussian. Or
Yes.
You must have multiple variables to give you the Gaussian.
It is, but it turns out that in order for the kicks to be big, you want to merge with the right orbital phase. So big kicks tend to be Gaussian. That was kind of my statement. And if you have, other cases here, these guys are not Gaussian. No, this guy here, there are many oscillations going on, and whatever.
And again, these axes, I'm still missing the basic picture here.
Okay.
You've got two black holes, one pointing, like one along the x, one along the minus axis, the spin axis.
Yes.
The orbital axis is along, I'm going to call that z.
Yes.
So your kick is z or x?
It's Z. In this case, it's Z.
It's in z?
Yes, it is.
Minus z.
Well, that depends on the orbital phase that you get. So that depends on whether you plunge like this or like this, or whether you start like this, or so. So you could, if you want, okay, let's look at this picture more carefully. So this green curve is right-left, meaning that one of the two black holes points towards minus x and the other towards plus x, and this one is left-right. So you flip the two things, and the problem is symmetric with respect to flipping the x-axis. So the final kick that you get, these curves are identical, but for a minus sign in z. Okay, so here is a comparison between this new surrogate way of extracting kicks and some old fitting formulas that were developed in the literature. So we claim, of course, that our method is more precise. Not really. This is more the RIT groups. That's the, this is Lusto 11, 13, or so. The two distributions broadly agree. We do have differences at large kicks. Like you see here, we underpredict, or they overpredict, depending on what take you. The fraction of binaries undergoing very large kicks. And well, we have discussions and suspicions of why this disagreement comes into. But the key point also I want to highlight with this slide is to, this distribution here was drawn taking just mass ratio uniformly, spin magnitudes uniformly and stuff. So how many black holes you have at what kicks is highly, that depends on what black holes you put into your distribution. And just to give a sense of scales in astrophysics, the typical escape speed of a globular cluster is 10 kilometers per second. It's probably down here. So virtually all black holes will be ejected by globular cluster. So if you have two black holes merging inside the globular, there's no reason, or it's extremely unlikely that the product of the merger remnant will stay inside the cluster. Even if they merge inside, the guy will get kicked out. The escape speed of a Milky Way is about here, and that starts depending on how exactly you build up this distribution. The escape speed of large ellipticals, on the other hand, is up here. So you really need to populate this tail to eject, say, a supermassive black hole from a large elliptical. So the question here that I want to move on to is, do superkicks, or these large black hole recoils, happen in realistic astrophysical environments or not? And here you need some serious astrophysical modeling to try and answer these questions. And that's, before I move on, this code to extract kicks and stuff is all open source and public, so you can install it, just in case you need kick to do whatever you want. It's a Python module, and it works. All right, so let's move on to the second part of the talk. Are superkicks real, and what can you do for modeling the astrophysical environment in which these things happen? So let me focus on supermassive black holes now. So the argument here goes as follows. So, okay, we got these numerical relativity simulations. They predict kicks of thousands of kilometers per second. Do supermassive black holes get ejected following a binary merger? Well, we kind of know that galaxies host supermassive black holes, and we don't see many binaries. We also don't see galaxy without a black hole. Where we look for a black hole, it's there. So how come? So if black holes merge, they're kicked out, we should see empty galaxies or so. So the standard solution to the problem is to align the spin. If spins are aligned, instead of largely misaligned as I was showing before, the typical kick speed is order of hundreds of kilometers per second, which is below the escape speed of a galaxy, and everything is fine. So maybe spins are aligned, and so you can avoid superkicks. So to go into this scenario here, I need to deal into two different phases. There's the astrophysics at large separation, and then gravitation wave driven in spiral at small separation. So to explain why this is the case, this is more almost textbook material, but just to put everybody on the same page. So let's step back a little bit and ask the following question. So can black holes really make it? So does that make sense that we see black hole mergers, so that we predict black hole mergers in the first place? So if you take the equations for the dissipation rate of separation A and eccentricity E at lowest post-Newtonian order, the scale as follows. These are standard quadruple formulas. And there are two key things that you can take out of these equations. So if you do dA dE, you find that the separation goes down, the eccentricity goes down faster than the separation. So if there's any in spiral, if there's any sensible in spiral, the binary tend to circularize by the time, so the separation.
Also, the dynamical range of the 7 major axes is much larger than the eccentricity.
Yeah, it is. So if you want to explain going down from, say, for supermassive black hole from a parsec to a milliparsec, by that time this eccentricity goes down by more than 3 orders of magnitude. So the other thing you can do is to take A dt dA, and this guy is basically a measurement of how long it takes for gravitation wave to dissipate energy and angular momentum, and you find that this guy scales with a very steep power of the separation A to the 4th. So reversing the same argument, you can calculate the typical separation, AGW, at which this time here is equal to an Hubble time. And what you find is that for a supermassive black hole, that's about 0.01 parsecs or so. So gravitational waves can bring a binary to a merger in less than an Hubble time only if the two black holes start from a separation of 0.1 parsec. That's much less.
Do you assume that both black holes are the same mass?
Yes.
So
It's an order of magnitude.
no, what I'm saying, how would this change for example, in supermassive black holes, you have the range of four orders of magnitude. So how would this change?
It's a factor of a few. It's these factors here. Right? This is from something ranging from 1 to 4 also. So it's up to a factor of 4. It's this q over 1 plus q squared. The eccentricity also changes a thing. If you have highly eccentric thing, that takes less to merge, of course. But order of magnitude estimates, so what I want to say is that you need both things. So gravitational waves can bring you to a merger if you start from some small separation, but galaxies in supermassive black holes will leave the binary at a much larger separation, order of magnitude larger than that. So to explain and to predict a successful merger, you need other things, so some astrophysical mechanism at large separation that dissipate angular momentum, bring the binary to the critical separation, this AGW, and from that point on, gravitational waves can lead to a successful merger. So to track how superkicks and how spin alignment, because at the end, solving the superkick problem means understanding spin alignment, you need to track both these phases, from the astrophysics to the relativity. So all the rest of my talk basically will be about gas-rich galaxies and how these evolve in disk galaxies and stuff, but I have one slide because I want to highlight one result on gas-poor systems. So if you look at big galaxies where there's very little gas around and stuff, these are the so-called BCGs, bright accelerated galaxies. These are the big ellipticals in the center of galactic clusters. These systems are, well, on the one hand, they're the bad guy. They're the worst system to look at superkicks because they have the largest escape speed. On the other hand, they merge a lot. So they grow in mass between a factor of 2 to 4 since at recent times. They have a high merger rate and have up to 4 major mergers since z equal 1 or so. So there are many major mergers, many occasions in which a merger can happen and a superkick can come out, and you don't have gas that tends to align the spin. So we played this game and showed that, well, in this plot here, there's as a function of the galaxy mass, this is the black hole mass, the population we injected is in blue up here. And by the time of, we let this merger tree evolve from z equal 1 to z equal 0, and that's a green plus red is the population of binaries that we get at the end. And note that the sum of the two, it's not 1, it's a bit less than 1, meaning that we do find some BCGs without a black hole at recent time. And also, this is here I split in my sample in the replenish fraction. So these are galaxies that, so there was a merger, then a kick, the binary got out, so the black hole got out, there was an empty galaxy for a while, but before z equals 0, this galaxy was replenished by another galaxy another black hole coming in from a galaxy from the same cluster. And you see that the predicted population here is systematically below the injected correlation line, that's what you expect. So 30-meter scale telescope or so might give us data in many BCGs and hopefully probing some superkick physics. This was a quick.
So this is like the population synthesis of galaxies?
It is. It's a simple.
How do you overcome the final parsec problem?
Oh, by magic. It just assume it happens. We just assume merger happens. We have a prescription for the delays between the galaxy and the black hole, scaling as 1 over t squared, which is basically a quadruple's formula.
Does this satisfy M sigma relation, or you don't?
Well, it's put in by construction. So we inject what?
You're putting initial M sigma.
Yes, we put in the M sigma as z equal 1.
But when it merges, does it?
Well, I don't have the plot for the M sigma, but that's the mass, bulge mass, black hole mass correlation. And you see, I mean, this is the line. So these lines here are the correlations I put in, and the non-replenished fraction just follows it. And that's because I'm keep on putting in things on the M sigma relation. And the replenished fraction, meaning a galaxy which was emptied by a previous kick and then replenished by a further black hole, is below because I don't have the previous black hole that keeps it onto the injected M sigma.
Is that too big a dispersion from that?
What?
Is that too big a dispersion?
No.
Not very well measured at that.
No.
What's the definition for a major merger?
We use 0.2 in Q, so mass ratio between the galaxies of 0.2.
And what does it imply for the mass ratio between the black holes?
Well, kind of the same because they're injected on a correlation relation.
So even at these extremes, so even if you take, so the largest mass ratio between the black holes is like factor of 5. So you...
Yeah, 5. I think it's 5 in these models. Yeah.
Kick velocity you get in this configuration.
For mass ratio of 5, must be order of 400s or so. But we get things which are 1-ish or so.
So it's not that all major mergers can inject a black hole?
No. I mean, this fraction here, if you, I mean, for 80% or so of the cases, nothing happens. So this means that you need order of, hundreds of good measurements of this to start probing this physics. Okay, so this was just a quick thing on BCGs. I really want to talk about disk physics now, because that's, I think, it's the environment where, which is most promising to confirm or rule out the occurrence of kicks. So in that case, you have phases of, long-lasting phases of accretion, and gas disks can align the spins. This is the so-called Bardeen-Patterson effect. So if you have a spin, a black hole, a spinning black hole, which is misaligned with respect to its own disk, like this at early time, so very quickly, length steering precession aligns the inner disk. So the inner disk, the torques from the length from the spin to the disk, the scale is the location of the disk to the third power. So very quickly, the inner disk aligns up to a point where the viscous time is equal to the length steering precession times, and that's the so-called Bardeen-Patterson radius. And further on, the disk maintains its own orientation. Now, on a longer time scale, the outer disk reacts and pulls the spin towards alignment with the outer disk, supposing that the outer disk is more massive than the black hole. And this thing scales on a time scale, which, as you see here, has, well, some disk parameters, so the aspect ratio of the disk, the alphas, A is the black hole spin, alpha 2 is the vertical viscosity, so how quickly warps are propagated through the disk, and m dot is the accretion rate of the disk that actually ends up being accreted onto the black hole. Now, the problem is that in a binary system, you don't have infinite time to do it. The spins is slowly aligning, well, slowly, this is like 10 mega years or so, is aligning, but at some point the merger happens. So there's not much going on. I mean, you don't have time to fully align the disk if the whole process is halted by the merger. And so the key point here is that, therefore, the accretion rates are all coupled to each other. So the in spiral, so the morphology overall that you get in this kind of system is the following. So you have a giant circumbinary disk, and in this case, you have a black hole here in the center, and a low mass black hole, so in this case, the mass ratio is very high, which is accreting and slowly opens a gap into the disk. This is a so-called planetary migration regime or so. If the mass ratio is kind of equal, the two black holes carve a proper cavity into the circumbinary disk. Now, the in spiral, so how quickly the merger is happening, is set by the properties of the circumbinary disk, and the alignment is set by the properties of this mini disk here. And that depends on how mass is actually streaming into the cavity and accreting onto the black hole. So we build up quick and dirty prescription to capture these effects. Basically, the in spiral timescale to first order approximation scales as the viscous timescale of the disk that sets the units. This term here, this is the gap opening. It's basically the same terms that the planet people have to study protoplanetary disk or so. And at high Q, you have a speed up because the center of mass, the potential well is deeper, basically. And then you can compare these three timescale. You have the two alignment, yeah. H over R is 10 to the minus 3 for a typical AGN disk.
That's the circumbinary part, right? What about the
Nobody really knows. These are dirty models, and we assume it's the same.
But is it a order unity near because when you get near the individual black holes, right? It's
probably the disk is probably puffier, but there are no well-precise modeling and stuff on this mini disk. I mean, there are something actually more recent than these results I presented. So in here, all disks have an H over R of 10 to the minus 3, which is a typical AGM value. Now, I agree that that's probably not true for the two mini disks. So you have three timescales in the problem, an alignment time, an in spiral timescale, which is this dashed line here, which is of order of 100 mega years or something, and 2 alignment from alignment timescale for either the primary black hole and the secondary black hole. So the takeaway message here is that secondary black holes always align. The thing is always below the in-spiral timescale, but there's a critical mass ratio, which is about 0.2 or so, at which the primary black hole does not align. The physical, so intuitively, physically what's happening is that the small black hole orbits closer to the edge of the disk, so it eats up all the material, and the primary starves. So there's not much mass coming into the primary black hole, and therefore alignment is highly suppressed. And so you end up, I mean, what we predict is that you might end up with supermassive black holes in which the secondary is aligned and the primary is misaligned. Yes?
So you start here at a separation of about a milliparsec?
Yes, it's at the fragmentation radius of the disk. That's where we start.
From further out. So how does the disk in the short time scale acquire?
I don't.
Sort of an ad hoc situation where you have 2 black holes.
At the fragmentation radius of the disk.
And then you have the disk around it.
Yes.
Black holes came from further out.
Yeah, that boils down to the final parsec problem, and so and now. I mean, this is again magic in a sense that we're taking a set of black holes at the fragmentation radius of the disk. The argument here is that if disk really solves the final parsec problem, the viscous in spiral, it's still the bottleneck timescale of the problem. So if there's some, star scattering and star before, it probably happens faster than the disk in spiral. But okay, all room for improvement here.
You assume that the orbital plane of the black hole binary is aligned with the disk. Is this a reasonable assumption?
It's an assumption. Yeah, I mean, this is all, I know. It's a dirty thing to do, but there's actually virtually the only model on coupling, disk alignment and in spiral timescale that is around. So better than nothing, I guess.
This mechanism would work if initially the orbital plane is.
You have another timescale. You need to align that first.
It's
Yeah.
clear to me that you would align it. No, it could be that you would just spiral without.
Yeah.
I mean, the AGN, basically dynamical friction as it's plunging through the galactic disk, that usually works to align with the galactic disk plane.
With the bind.
Yeah, that's like a very old paper by like he talks about like grinding of stars or something, right?
There's also a paper by Ivanov or so that studies this thing.
It seems to me that the stars, because in our galaxy center you have different populations of stars that aren't. There's not much of a disk, but they're spinning in different directions and different. It's not clear to me that the dynamic friction will do it.
Well, it's more aerodynamical drag. It's not as much aerodynamic, or at least that's what Barnary's argued. So why are you using H over R so small here?
0.2?
Well, that's the alpha.
Oh, that's a typical AGN disk value, isn't it? Or maybe?
Yeah,
So AGN disks are thin.
Okay, yeah.
If you're near Eddington, the ADA part gets to be higher.
Yeah, and
Without
so-
the clock.
Yeah, but when you're computing these timescales, you're looking at each of the disks around this.
And I assume that all disks have this aspect ratio, and that boils down to your earlier question.
I'm not sure. Yeah, so if you make that H over R significantly bigger, those timescales are going to be dramatically different, and also you're not going to be able to use
The scale as H over R at the warp. So this W is evaluated at the warp radius to the 2/3, the alignment, the spiral timescale. No, the alignment timescale. Sorry. All right. So how much time do I? Okay. Well, I'll skip all the end and just go to one more message. So we prevent small secondaries. We prevent the small secondaries might prevent their. We predict that small secondaries might prevent their primaries from aligning. Now, this is at the coupling radius, if you want. So where the disk stops being, the disk will leave you black holes with some misalignment, but then by the time they merge, there's a whole relativistic in spiral these guys have to go through. So at some point, gravitational waves becomes more powerful than gas, and that happens more or less at the coupling radius, which is order of hundreds of or thousands of gravitational radii of the binaries. And here, it's vital to track the binary through a long series of post-Newtonian precession cycles. So what's happening is that the two spins, there are spin-spin and spin-orbit couplings. So the orbital angular momentum and two spins are all coupled to each other. And the whole system precesses about the direction of the total angular momentum. So this is important, of course, for gravitational wave people. And that's because the waveform that is emitted has a very different signature if the spins are precessing or not. If spins are aligned, you have the usual chirp that you see. And if spins are precessing, because the gravitational waves are beamed along the direction of the orbital angular momentum, you see this very distinctive modulation that comes like more or less a lighthouse effect when the orbital angular momentum, the tip of the angular momentum passes through the line of sight or so. So it's useful here to define a couple of quantities. So let me define a bunch of angles. I'll call, if you put the orbital angular momentum on one axis, I'll call θ1 and θ2 the angles between the two spins and the orbital angular momentum, and delta phi the angle between the, so you take the two spins, you project them onto the orbital plane, and you take the angle between those two projections. So what I want to go through is what's the effect of all these complicated precession dynamics onto the black hole kicks. And so here is a series of black hole binaries that I evolved using 3.5 post-Newtonian equation of motion. So here, this is just an exercise. I'm picking a binary, so sample of binaries which are isotropic in the two angles. So at initial separation, which is some 10 to the 4 m or so, all the binaries are, I have a grid in this space here, and then I let these guys evolve down to 10 m, so very close to merger or where the PN approximation breaks down or so, and you see that more or less nothing terribly exciting happened. The distribution is isotropic at the beginning and stays isotropic all the way to the end. And this is an old result that dates back at least 2007 or so. Now, and this is the same evolution shown in this variable delta phi, which is the projection of the two spins onto the orbital plane. Now, this is the same picture, but where I'm just coloring the binaries. So here I color the binaries according to this bisector here. So red binaries are the binaries for which the primary black hole is more aligned than the secondary, and the blue binaries are the binaries for which the secondary black hole is more aligned than the primary. So in this θ1, θ2 plane, things mixes up, and again, nothing interesting happened. The important part is down here. So you see that the red binaries, this is delta phi, so the red binaries tend to cluster about delta phi equals 0, and the blue binaries tend to cluster about delta phi equal pi. So below here, there's a kind of interesting dynamical phenomenon, which is some resonant configuration. So these guys here, delta phi equal pi, 0 and pi, they're the so-called spin-orbit resonances of the post-Newtonian problem, were discovered back in 24 and then explored to the death by us and other. And the key point here is that there's a critical dependence on the initial condition. If a binary starts here in this variable, it's more likely to be found with delta phi equals 0. If a binary starts here in this tilt variable, a binary is more likely to be found with delta phi equal pi. All right, so what's the consequence on the kick on all of this? Well, if you have binaries which are close to pi, that's close to the superkick configuration. So you expect bigger kicks for a specific region. You expect the bigger kicks should come from a specific region of the parameter space. And so these are preliminary results by my undergraduate student, Luca Reali. And he's basically filtering, showing. So in this histogram you have, for a sample of binary, again, isotropic and all the rest, but this is just for illustrative purposes. You have all the binaries in this black histogram, and then we classified them according to how close they are somehow. I mean, there's a proper classification here, but for now, so red binaries are the ones that end up being close to delta phi equal pi. Blue binaries are the ones that end up being close to delta phi equals 0, and the green binaries are the ones that circulate from pi to 0 all the end. And as you see, all the big kicks down here are basically all red. So there's one of these spin morphologies which actually has a proper dynamical classification. Only one of these family can predict large kicks. So, well, this is some interesting preliminary results. What's the consequences on all this disk physics that I've been explaining? And this is all contained in this plot. So what we are doing here, I took an isotropic sample of black hole binaries with Q equal 0.2, that if you remember was that turning point where primary black hole starts being misaligned. I locate the binary in the θ1, θ2 plane. Those are the tilts between the spin and the orbital angular momentum. So I give him a value at the decoupling radius, say here. Then this binary will move around in this plane, and I color this point according to the kick. And all of this complicated PN dynamics comes in, but the net effect here is that big kick, so all these red points are up here. And this region here is precisely where the secondary black hole, θ2, is aligned, and the primary black hole is somewhat misaligned. So we do predict big kicks in the right place, coming from disk physics and fitting into all this PN stuff. So maybe super kicks in gas-rich galaxies are more common than previously thought, and seriously, as all the discussion here already prompted, more work is needed actually to quantify and clarify these claims more carefully. So I had one more point, but maybe I don't have time. Or if you want, I'll go through it very quickly. OK, I'll go on. So one more thing is always still about black hole kicks. Can we detect kicks directly somehow with gravitational wave data? And here the idea is that so when you measure the phase of a gravitational wave, the mass and the redshift are completely degenerate. So what you really measure, if you look at so what the LIGO folks do is that from the phase of the wave, they actually don't measure the total mass of the system, but the redshifted mass, or the so-called detector frame mass. And then from the amplitude of the wave, that gives you information on the luminosity distance. They assume a cosmology, go from luminosity distance to redshift, and break the degeneracy in the phase. So you're really measuring this, and that's because the binary is going away from you because of the expansion of the universe. Well, if you have a kick, the binary is actually recoiling away or towards you. So what you're really measuring is not the total mass of the system, but rather the total mass times the velocity projected along the line of sight. So this is this idea for an extremely exaggerated kick of half the speed of light. So this is a tiny effect in terms of the kick, in terms of the speed of light, even 1,000 kilometers is like 1% or so. So it's an absolutely minuscule effect, but on an highly exaggerated case of half the speed of light, what you get is that if the binary is recoiling away from you, much like the cosmological case, the shift goes, the signal is redshifted, or if the binary is coming towards you, the signal is blue shifted. Now, critically, there's a time dependence here. In the early part of the in-spiral, there's no kick going on, so there's no redshift here, and all the redshift builds up close to the merger phase, like we saw before. So it's not really a true degeneracy, because you can leverage the time dependence to break it. So let's do an order of magnitude calculation, so to quickly estimate how big this effect is. So, OK, you have 3 standard phases, 4 phases with a kick. The 2 binaries are in-spiraling, they merge. There's the ring down part, and well, maybe the final guy is kicked somewhere. So let's assume we break the signal into an in-spiral and a ring down part. So assuming the mass from the in-spiral is measured extremely accurately, the mass that you get from the ring down is the in-spiral mass times, well, there's some radiated energy, which we can model accurately, and a kick term, like here, which again is the projection of the kick along the line of sight. So assuming this term has 0 errors, to measure this guy with the precision, so to measure an effect on here, which is of 1% the speed of light, you need to measure the ring down mass with the precision of 1%, order of magnitude. Which means, again, order of magnitude, an SNR, a signal-to-noise ratio order of 100 in the ring down only, in the ring down part of the waveform. And this is tough. For 150914, which was a very loud source, the ring down SNR was like 4 or 5. So we are talking about, I don't know, 20 times louder than 150914. So an experiment which is 20 times better than initial LIGO. So that's going to be tough, if not impossible for LIGO. But hopefully, future ground-based detector and LISA, the space mission, will be able to make this measurement. So here is the same argument for a population of black hole binaries now. So to make it a bit more quantitatively, what we are doing here is that we take a waveform from a black hole binary, and we kick it. So going from H0 to HK. You can compute the SNR of the waveform and the match or overlap, so how close they look like in the detector. And a very rough criterion for distinguishability is this guy here. So if the overlap is small enough, it means that the 2 waveforms are sufficiently different from each other, they can be tell apart. And so binaries, this is in this overlap SNR space, binaries which are above this line, they have a kick which is distinguishable. And as you see, there's nothing for typical LIGO population. And there are about 6% of this particular population for LISA. And many of them has these red kicks, which are the super kick of 3,000 or so kilometers per second I was hinting at before. And we found similar number for third generation detectors. So LISA has the potential to directly measure black hole recoils. And I'm done here. I just want to highlight two very recent development of this idea. So very recent, the paper from the Georgia Tech group, they basically showed that, they basically took our study showing that, as I was showing at the very beginning with this carry phase, the kicks are encoded not just in the difference between the 2 and -2 mode, but also in higher order modes. By measuring higher order modes, you can actually bring that SNR threshold to detect kicks sensibly lower, claiming even a possible detection at SNR as low as 15, which would be very promising. Something we are doing, and this is done by Katie Chamberlain, which is an undergraduate that worked with me last summer at Caltech. We now have an analytical recipe to implement Doppler shift into any waveform model. So you give me a waveform model, and I can Doppler shift it with whatever Doppler profile you want. And that's useful not just to do kicks, but say you have a binary which is orbiting about a tertiary companion. That will produce a Doppler shift onto the emitted waves. And this is a completely analytic and generic procedure to implement it that we achieve crazy high precisions. All right. So before I want to finish, so measuring superkicks directly would be a measurement of fundamental interest in a sense that much like the Hals-Taylor pulsar provided the first evidence that gravitation waves carry energy and angular momentum, so shrinking the binary system. 150914 provided evidence for the gravitation waves themselves. A direct measurement of a kick would provide direct evidence that gravitation waves carry linear momentum. Now, we believe in GR, and of course linear momentum emission has to be there, but this would be direct evidence, if you want to call it. So I'm done, and sorry if I'm slightly over time. So I hope I convinced you that black hole kicks are something cool to study. I went a bit into the derivation and the modeling of black hole kicks from waveform model, into the astrophysical modeling of things, especially how coupling disk physics and post-Newtonian evolution, you can actually predict large kicks in the right place, and then hinted at some prospects for performing direct detections of this phenomena. And thanks for giving me the opportunity.
Okay, so we had a bunch of questions, but does anybody have follow-up questions or?
Sure.
So there's a class of dwarf galaxies called ultra-compact dwarf galaxies that I thought one of the ideas was that they form in this way, that you had a merger and then I was ejected and it basically took with it everything was within a Bondi radius. So is there a way to...
is this NG1927 or something? Okay.
There's a whole class of them. So I'm wondering if there's a way to verify that this is the origin is indeed
in this.
merger.
I never, I don't know enough observational astronomy. So I know there's one event, probably NGC 125 or something, which is a BCG, which has an undermassive black hole. So, which is below the bulge mass relations or so. And one of the explanations, after we put out this BCG paper, some of the observers came to us and say, oh, maybe, we have this undermassive black hole, so maybe there was a kick or so. And that's...
The usual problem with the BCGs is their holes are even bigger than you'd predict from an Orion.
I see. They're too big?
They're
or
too massive.
Okay.
The measurements are not exactly great.
Okay.